If we fill a balloon with compressed air, there is a greater pressure within the balloon than outside. When we release the air within the balloon, the column of air escaping sets up a momentum going in one direction, and the reaction in the other direction, acting as pressure on the interior of the balloon, propels our little rocket. If we look at a representation of a rocket engine's thrust chamber, we see the same principle applied. Through combustion in the thrust chamber, great amounts of energy are released. Hot, expanding gas escapes through the nozzle throat. Because of the design of the nozzle, the mass of escaping gas molecules is accelerated rapidly. This kinetic energy, bursting from the nozzle exit at supersonic speed, generates an enormous force. From the mass and acceleration of the gas flow is computed a basic measurement of rocket power, thrust. The reaction to this thrust is expressed in pressure against the top of the chamber here, against the sides here, and against the interior walls of the nozzle here, forcing the thrust chamber, and with it, the entire body of the rocket upward.
Okay, so here we're going to do a little bit of science to prove once and for all if, in fact, rockets move by pushing off atmosphere behind them, or pushing off of anything behind them, or if they move through Newton's third law, which states everything has an equal and opposite reaction, or every action has an equal and opposite reaction, and by just the process of expelling something out of the back, you gain forward momentum. So, we'll add our weights to the cart, and we'll redo our experiments to make sure it can move under its own weight. Test 1. Movement was observed. It would also behoove us to observe the fact that with added weight, it did move significantly slower than it without weight, which we can test again by removing the pennies. Let's verify that it is 29 grams lighter. 107. So that corroborates with our 104 gram cart and the 103 gram balloon, making 107. So without weight, with weight. Significantly slower. In fact, it couldn't even propel itself off of our testing surface. So, that was 2 tests with the weight, so let us test again for 3. Four. And finally 5. So, we know for a fact that it can move itself forward by using just the force of this balloon. So, what happens when we introduce our vacuum to the back of it? So, test number 1. Ooh. Movement was still observed. Test number 2. Movement was still observed. I did notice it was a little bit slower than without the vacuum. Test number 3. Movement was still observed. Seemed to have been about the same distance as without the vacuum. 4. No movement observed. 5. Movement observed. And since we had one test that did not move, let's do a few more, just to make sure that we are getting accurate data, and to see if it happens any more times. So let's do an extra 3. Test 6.
One other thing. Many people in the past thought that the rocket required a solid body of atmosphere to push against in order to move. Incorrect.
So Newton's third law in action. So now to the interesting part, because I'm going to demonstrate in this next test that a mass most certainly is required to make a rocket move, or a balloon move in this case. So I'm just going to put up on the screen again the quote that the guy made earlier that I asked you to remember. It doesn't need to be able to push on anything to make it transit, is what he says. So I've taken a piece of paper and I've wrapped it around the rear end of the balloon and taped it top and bottom. So the nozzle is sort of in the curve of the paper there. So when I let go, the air will still escape from the balloon at the same speed. The balloon will deflate as quick as it did without the paper. So according to his quote earlier, this should still move, this should still transit at the same speed, because it's not reliant upon it pushing on anything. It's the mere fact that air is released from the nozzle that provides the reactionary force to propel the balloon. So let's have a look at what happens. So Newton's third law experiment, test 2. Well, that didn't move very far. Let's try another one. So Newton's third law experiment number 3. Newton's third law experiment number 4. Not looking good. Okay, Newton's third law, 5th and final test. Come on, we've got to see some movement. And just to show that there's no restriction whatsoever. Now you may have noticed that in a couple of the tests the balloon actually rotated around the string, sort of radially. What was actually happening is the air escaping from the balloon was disrupted by the paper, and it was disrupted such that it was pushing air unequally from either side of the paper, because I haven't put the masking tape and the paper on exactly square, exactly perpendicular and centrally to the balloon nozzle. It created an imbalance, and it was pushing the air out of one side and caused it to rotate around the string, not in the direction that Newton's third law states that it should, which is the opposite direction to which the air is escaping. So let's have a look at the rocket engine nozzle. And Wikipedia, let's scroll down to atmospheric use. The optimal size of a rocket engine nozzle to be used within the atmosphere is achieved when the exit pressure equals ambient atmospheric pressure, which decreases with altitude. So atmospheric pressure is air pressure. So right there in that first sentence they are saying that rocket nozzle design and efficiency of such is dependent upon the ambient atmospheric pressure, the air pressure, which decreases with altitude. So for rockets travelling from the Earth to orbit, a simple nozzle design is only optimal at one altitude, losing efficiency and wasting fuel at other altitudes. So what they're saying there is, in an ideal world, they would have a nozzle that changes its shape and its dynamics as altitude increases, because there's only, if it's a fixed shape, there's only one altitude at which it's at its optimal. So let's go down to the vacuum use. Now, the whole premise of this video is that I don't think rockets can work in a vacuum. So the first sentence that it says here, I think, is applicable if you remove the word vacuum, because it describes high altitude. So let's read it. For nozzles that are used in very high altitude, it is impossible to match ambient pressure. Rather, larger area ratio nozzles are usually more efficient. So right there they're saying that at high altitude the ambient air pressure is so negligible that they need to put much larger ratio nozzles on to account for the loss in air pressure. So again, air pressure is small at high altitude, therefore larger area ratio nozzles are more efficient. If you take this to its logical conclusion and traverse into space where air pressure is zero or very near to zero, how big or what area ratio nozzle are you going to need then? Would this be infinite? Do you see what I'm saying? So if we go back to look at what NASA claim on their Rocket Principles webpage, they claim on the ground the only, and I must stress that word that they use, the only part air plays in the motions of the rider and the skateboard, or in our case the rocket, is to slow them down. Moving through the air causes friction, or as scientists call it, drag. So they are claiming that the only part air plays with rockets on the ground in the Earth's atmosphere is the drag effect that's caused by friction on the body of the rocket itself. Nothing to do with the propellant dynamics. So they are claiming the exact opposite of what Wikipedia are telling us, because they're telling us that there's only one altitude at which a particular shape nozzle or size nozzle is optimal, and that they have to actually increase the nozzle ratio as altitude increases.